Welcome to Applications and Derivatives, Lesson 9, Linear Approximations and Differentials. These are a couple of old school, really they're old school problems before graphing calculators came on the scene. I figure someday these two topics will not be an AB topic any longer. Right now they are, so we'll cover them. Linear approximations are a way to try to make a guess of a certain number using the derivative and tangent line approximation. And then differentials are a like a percent error kind of thing, how much a figure can be off depending on how much the length differs plus or minus. So let's go right on into linear approximations. Your first example, linear approximations, is estimate the cube root of 26.9. Okay, we should know that our guess is going to be just a little bit less than 3 because the cube root of 27 is 3. So this is 26.9. Our answer should be just a little bit less than 3. So let's go at it. You ready? We're going to start with y equals a function of x. Guess what function it's going to be? It's going to be the cube root. We'll translate that to y equals x to the 1/3. And now we're going to take y prime. Y prime equals 1/3 x to the negative 2/3. So y prime equals 1 over 3 times the cube root of x squared. And we're going to pick something close to a 26.7 that makes sense for us. We're going to try 27. So we're going to find y prime of 27. That equals 1 over 3 times the cube root of 27 squared. Cube root of 27 is 3. 3 squared, 9. So y prime of 27 equals 1 over 27. There's our slope for our tangent line. And how about what is y of 27? Y of 27 is 3. So our tangent line approximation, y minus 3 equals 1/27 times x minus 27. There's our tangent line. Let's put it in slope-intercept form. Y equals 1 over 27x. When I distribute that, I get 1. So minus 1 plus 3. That would be plus 2. Now we're going to use that tangent line to approximate what the cube root of 26.9 is by going y equals 1 over 27 times 26.9 plus 2. So 26.9 is not actually on the cube function, it's on the tangent line function, but we should get really close. So let's see here, that would be y of 26.9 equals that. So y equals, hold on a minute, I can't read my paper. I'm cheating, yeah, I know. Alright, 2.996296. Hey, that's not bad because when I actually put it in the calculator was 2.9962917. Oh, that's really good approximation. Probably good for what we need. Alright, let's move on and let's look at another one. We want to estimate the sine of 2 degrees I don't want to have to deal with degrees, so I'm going to change that angle to pi over 90. Multiply 2 times pi over 180, pi over 90. So we are going to start out with y equals sine x. We'll take the derivative, y prime equals cosine of x. Alright, that 2 is really close to 0, or the pi over 90 is really close to 0. So we're going to find a slope right now. Y prime of 0 equals cosine of 0. Y prime of 0 equals 1. And what is y of 0? We need a point. Put 0 in here, we get 0. So our equation is y minus 0 equals 1 times x minus 0. Simply put, y equals x. So y of pi over 90 equals pi over 90. And that equals, according to this, 0.034907. And when you actually put it in a calculator, 0.034899. That's a great approximation. Let's go ahead and move on to the next function. Okay, now we're doing differentials. Estimate the possible error. That would be error in the volume. That would be dV. The possible error in the length of the side is dx. So what we're going to do, it's a lot like differentials is a lot like implicit differentiation. All we're going to do is we're going to take the differential, or the error in the volume, equals, take the derivative with respect to x, 3x squared, and times the error in the length, dx. So dv equals 3 times 14 squared times 0.3, and that makes the difference in the volume where are we? Yes, 176.4 centimeters cubed. That's how much of the volume could differentiate, or error. Let's go ahead and move on to example 4 with differentials. Okay, estimate the possible error in the area of a circle. The radius is 3, and the radius may change anywhere from 1/100th. So dA, the error in the area, equals 2 pi x dx. So the differential in the area is 2 times pi times x, which was 3 times 0.01. So the error in the area is 0.18850 square inches. And let's go ahead and move on to the next one. Okay, estimate the possible error in the area of the triangle. That triangle has a hypotenuse of 4 light years. This is a huge triangle. Alright, let's go ahead and set it up first. Let me see if I can draw that. Come on, I did already. There it is. I already did draw it, actually, because I didn't feel like doing it in front of you. So let's see here. If this is x, the hypotenuse, what's the length of each one of these sides? Wait for it. Come on, it's 45, 45, 90 triangle. X over root 2. That is correct. And then what's the area of that triangle? The area equals 1/2 times that side squared, x over root 2 quantity squared. So let's simplify that a little bit, please. Area equals 1/2 times x squared over 2. Area equals x squared over 4. So now we're ready to take the derivative. The difference, or the error in the area, equals 2 over 4 1/2 x dx. So that would equal 1/2 times 4 times 0.025. So the difference, or the error in the area, equals 0.05 square light years. That still seems really big to me. Anyway, that is Applications and Derivatives, Lesson 9, Linear Approximations and Differentials.